Enterprise storage arrays using NAND flash dominate TPC-C results, but few match Violin's consistent response times. I met with Don Basile, CEO of Violin, a PhD formerly of Bell Labs, to discuss how Violin's architecture achieves this. Here's Don.
The first foundation of that is saying, listen, NAND itself is not a media that gets better. NAND itself is a media that gets worse. So as the generations go, it gets slower, not faster. But it's a chip technology. Yeah, it's a chip technology, but it's not really. But it is. And so it's going to slow down. It gets more error prone. Okay? And it gets harder and harder to program in the sense you have to do things at much, much bigger scale at the same time. So unlike a memory cell like DRAM, which is just a nice small cell, it stays the same. The NAND, you start to have multi-megabyte and tens of megabyte pages. But I wanted to write 4K data. Well, guess what? Too bad. Go program 32 megabytes to do that. It becomes more and more inefficient. Violin has 4 layers of hardware control technology. So we make the chips, 4 layers of chips, ASICs. They go in our device that lets us get more performance with lower latency for less cost out of a flash system than anybody else.
Violin's 4-level architecture separates essential activities in a layered model. Violin's flash controller is tightly integrated with the Toshiba flash and the higher layers. One integration benefit: upper layers give controllers hints to minimize latency, improving performance 2 to 5 times. The Violin Intelligent Memory Module, or VIM, is the next level. VIMs form a mesh network via 3 ports, automatically failing over to hot spares with no performance impact. 5 VIMs form a vRAID group. The third-level vRAID controllers manage RAID stripes and flash housekeeping across the system's 12 vRAID groups. Any vRAID controller can access any VIM. A 4th-level array manager directs traffic to the vRAID level across a low-latency, non-blocking switch. How does this work in practice? A 4K write comes into the array manager on Fiber Channel, InfiniBand, or 10 gig Ethernet, directed to a vRAID controller and striped across 5 VIMs, 4 data, 1 parity, and written by the flash controller. A 4K block is always available to be read because the system only needs 4 of the 5 VIMs to read data. If needed, the parity rebuilds the data. Slow flash erases can lead to wildly variable 10x or more latency. vRAID housekeeping, garbage collection, and block management ensures free blocks for spike-free writes and erases. During housekeeping, writes are buffered for a few milliseconds until written. This technique is key to Violin's consistently low latency. Violin's architecture has a remarkable impact in the face of declining flash performance. Here's Don again.
Our systems, as we've shown, between the 3000 and 6000, use less NAND chips in the 6000, but are 4 times faster than the last one. So we used less media, but we got faster. And the media got slower. We still got faster. Right? And that's really where the Violin technology around vRAID comes together.
The StorageMojo take. Violin Memory aims at the high-end storage market, now dominated by slow, costly, and inefficient disk arrays. Violin is a clean-sheet rethink of array architecture, using flash to create fast, compact, efficient, resilient, and consistently low-latency enterprise storage. Almost all TPC-C benchmarks for the last 2 years are flash-based. These benchmarks show Violin arrays have very low and consistent latency. System architects planning mission-critical transaction systems should give Violin a close look. For StorageMojo, I'm Robin Harris.